Now, let us discuss about discrete Fourier transform. We have already seen that given a continuous time domain signal x of t, as it cannot be processed by computers, we get a discrete time domain signal as x of n, whose frequency domain representation is given as x of e power j omega. From this, we see that the signal x of n, though discrete time signal, x of e power j omega is continuous. So from this we see that as x of e power j omega is continuous, it cannot be processed by computers. So we come up with another type of frequency representation called DFT. So the DFT, which is represented as x of k, is the sampled version of x of e power j omega in the range of minus pi to plus pi. From this, we see that the DFT analysis equation can be written as x of k is equal to sigma n is equal to 0 to n minus 1 x of n multiplied by omega n power minus kn, where omega n can be written as e power j 2 pi by n. Also, please note that the k runs from 0 to n minus 1. So if there is a signal x of n of length n, its DFT x of k is also of length n. So whatever equation we have written here is analysis equation. Now we write something called synthesis equation, which is mainly to get the original signal x of n back from given the DFT, which can be written as x of n is equal to 1 by n sigma k equal to 0 to n minus 1 x of k multiplied by omega n power kn. Also, so this is synthesis equation. Also, as discussed, x of k, that is the DFT, can be written as equal to x of e power j omega, where omega is equal to 2 pi by 2 pi k divided by n. So for any value of k, the DFT value can be obtained as x of e power j omega, where omega is equal to 2 pi k by n. Please note that in case of DFT, to get a particular x of k, the number of multiplications required is n, that is between x of n and omega n power minus kn. So to get a particular value of x of k, we require n complex multiplications. From this, we see that to calculate the DFT series x of k, which is actually n values, the total number of complex multiplications required is n into n, which is n square. So the computation of DFT has an order of n square, so which is quite complex. So from because of which now we will look into another way of implementing DFT, that is through FFT, which means fast Fourier transform. Please note that in case of fast Fourier transform, the number of multiplications required is order of n into log of n to the base 2. That's why implementation wise FFT is preferred than DFT. However, please note that DFT and FFT give same output. Now we will discuss about some of the salient points as related to FFT. FFT, the number of complex multiplications in FFT is of order of n into log n to the base 2. This is mainly achieved through butterfly architecture in FFT, which mainly avoids any duplicate processing required. Each butterfly architecture requires one multiplication. Also, please note that in FFT computation, for computing the FFT for a sequence of length n, there are totally log n to the base 2 stages, and each stage requires n multiplications. That's why in case of FFT, the number of complex multiplications is of order of n into log n to the base 2. Also, FFT can be achieved through in-place computation, which is mainly helpful in saving the memory requirements. So, so FFT can be mainly computed through two ways. One is decimation in time, other is decimation in frequency. So from this we can say that there are two ways in which FFT can be computed. One is decimation in time algorithm and other is decimation in frequency algorithm. Now let us discuss about another topic, which is correlation and covariance. Given any signal x of n which is real and stationary, its autocorrelation function Rx of m is defined as expectation of x of n plus m multiplied by x of n, where xn plus m is shifted version of xn by m. Similarly, the autocovariance function is defined as Cxm is equal to expectation of xn plus m minus mx multiplied by xn minus mx, where mx is the mean of the signal xn. So it can be written as expectation of xn. Also, please note that if m is equal to 0, Rx of 0 is equal to expectation of xn square, and Cx of 0 is equal to expectation of xn minus mx whole square, which can be written as variance of xn. Also, if mean of xn is equal to 0, that implies Rx of 0 is equal to Cx of 0. From this we see that given a signal xn of n which is real and stationary, we defined the autocorrelation and covariance functions. Then we looked into a special case of shift by m is equal to 0, where Rx of 0 is equal to, sorry, where Rx of 0 is equal to expectation of n square and Cx of 0 is equal to variance of xn. If mean of xn is equal to 0, Rx of 0 is equal to Cx of 0, which is equal to variance of x. From above, we can say that the power spectral density of the signal xn of xn is given as px of e power j omega, which is Fourier transform of Rx of n. As Rx of n is a discrete signal, px of e power j omega is obtained by dtft of Rx of n. From this, we can write that px of e power j omega is equal to sigma n equal to minus infinity to plus infinity Rx of n multiplied by e power minus j omega n. Also, Rx of this is analysis equation. Also, Rx of n can be obtained from PSD as 1 by 2 pi integral minus pi to pi px of e power j omega multiplied by e power j omega n d omega. This is synthesis equation. The analysis equation is mainly helpful for getting the PSD from autocorrelation function, and the synthesis equation is mainly helpful for getting the autocorrelation function from PSD. Now, let us look into some of the examples related to DFT, FFT, and PSD, that is the power spectral density function. Let us consider a signal x of n which is equal to 1, comma 2, comma 3, comma 4 if DFT of the signal x of n is given as x of k, find x of 0. We know that the DFT of the signal x of n is given as x of k is equal to sigma n equal to 0 to n minus 1, that is 3, because the length of the signal is 4 here. X of n multiplied by omega n power minus kn. We know that omega n is equal to e power j 2 pi by n. As n is equal to 4, we see that omega n is equal to e power j pi by 2, which is equal to j. But for x of 0, we substitute k is equal to 0 to get x of 0 as sigma n equal to 0 to 3 x of n multiplied by 1. From this, we see that x of 0 is equal to just the sum of all the samples of x of n, which is equal to 10. From this, we see that in DFT representation, x of 0 is equal to 10. Now, let us consider another problem as per which the autocorrelation function of a signal x of n is given as 1 by 2 whole power n u of n. From this, find the PSD of the signal x of n. The PSD of the signal x of n is given as px of e power j omega, which is actually the Fourier transform of Rxx of n. So this can be written as sigma n equal to 0 to infinity 1 by 2 whole power n e power j minus j omega n. This can be written as sigma n equal to 0 to infinity 1 by 2 into e power j omega whole power n. Yeah, the signal 1 by 2 whole power n u of n is absolutely summable. We see that the PSD can be simplified as 1 by 1 minus half e power minus j omega. So we see that for the given autocorrelation function, the PSD can be obtained as 1 minus half e power minus j omega. Now let us consider another problem as per which it is given that the PSD of a discrete time signal as is given as px of e power j omega is equal to 1 minus mod omega by pi. This is for mod omega less than or equal to pi, 0 otherwise. It's given that the mean of the signal x of n, that is mx, is equal to 0. From this, we need to find the variance of the signal x of n. We know that autocorrelation function of the signal can be given as Rx of n is equal to inverse Fourier transform of Px of e power j omega. From this, we can write that Rx of n is equal to 1 by 2 pi integral minus pi to plus pi Px of e power j omega multiplied by e power j omega n d omega. Upon substituting n is equal to 0, we see that Rx of 0 is equal to expectation of x square is equal to 1 by 2 pi integral minus pi to pi px of e power j omega d omega. Upon plotting px of e power j omega, we see that it's a triangular PSD which is present in the range of minus pi to plus pi as shown in the figure with a value of 1 at omega equal to 0. From this we see that Rx of 0 is equal to 1 by 2 pi multiplied by half multiplied by 2 pi into 1. This half multiplied by 2 pi into 1 is the area of the PSD with omega axis. From this we see that expectation of x square is equal to half and mx is equal to 0. That is the mean of the signal is 0. From this, the variance of the signal x can be written as expectation of x square minus mx square, which is equal to half. So the variance of the signal with the given PSD and 0 mean is half.